Okay. All right. Okay. So today we are going to move on into model and techniques for geometric modeling. So basically, what is this all about? All right. So you would have actually gone through concepts of design, right, in chapter 3 in the last two classes. So this chapter will speak about the models and the geometric modeling techniques. So basically, this chapter is going to describe things that you are doing in your lab in CATIA. So basically, what are we doing in CATIA? We're actually modeling, isn't it? So we have done 2D and we're going to do 3D, drafting, assembly, and multiple things. Okay. So it will discuss the concepts of theory behind it. So it will be a lot relevant, and maybe it will resonate to you better if you actually, if you've been through those sections in lab class. Okay. So the first topic over here, first slide over here actually tells us the need for the geometric model. Basically, it stems from the concept that there is an idea that forms in the geometric model. So before that, I apologize. I don't have a touch pen, so I'm using mouse. So please pardon my writing, and it may not be so beautifully syncing. Okay, so it comes from an idea, all right, of a model. So basically, geometric model means we are moving towards design, and the design comes from an idea. So can someone tell me why are we even actually having the need to do design? Anyone? Anybody? Why are we actually having the need to make a design for that matter? So why is this
best
geometric?
best
Yeah.
quality for the product,
Sorry, can you repeat?
to create the best quality of a product.
Okay, to create the best quality of a product. Why do we need to create a product based on the certain design that we are deciding?
User specifications, I think.
No, why are we needing to make that product? Why do we need to make a particular product, whatever the product is?
To make life easier.
Make life easier. Okay. And so making life easier means what was there that 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 brought about the need to make life easier? There was a demand, right, to make life easier. And the demand arises from the fact that there is a problem, basically, all right, a problem that you want to address. So based on the fact that there is a problem that you want to address, bringing about a demand will bring about ideas to solve that problem and address that demand. And the ideas needs to be realized or displayed or presented. And how is that done? It is done through the geometric modeling in our current environment. Now, if you talk about in the past, in conventional modeling system, it is turned out, you model your geometry, but it's just not done in the computer environment. Okay. So once that design is made, right, your model is made, your model can be used to actually design and analyze the entire condition or situation with the model. So you're talking about it. What do we analyze? We analyze the design concept, the design functionality, the design integrity or product structural integrity, and then we see, whether it can withstand stress, strain, heat, everything, multiple concepts. Then we analyze whether it can be assembled, manufactured, so multiple host of things, right? Before we actually finally bring it to production. So our geometrical modeling is the center, right, for these concepts, without which we don't have a business, right? As far as engineers are concerned, everything has been modeled, isn't it? So this is where the design engineers or the design concept comes into play. So the functions of geometric modeling itself in the design area, all right, is in your CATIA, at least you can view it from that point of view. Under the design mode, you can actually evaluate areas, volumes, right? Mass property, inertia property.
Middle mic.
Oh dear, sorry. When was it muted? Can you last tell me what I said?
Just now.
Okay, so This slide, from this slide onwards,
Yeah, yeah.
okay. So the functions of, wait, let me minimize this. Okay. So the functions of geometric modeling, right? In our design area, basically you can relate it to CATIA, right? Under design, we can evaluate areas, volumes for our model. Like you can imagine if this was your model. And then you can evaluate mass property, inertia. So all mechanical properties can be evaluated. Then if you have an assembly, you can check the interference in the assembly, right? Tolerance in an assembly, and then in that assembly itself there is any kinematic motion, so you can actually simulate that and you can generate mesh for finite element analysis. Under drafting, you can check cross-sectioning of a product if you want to see the cross-sectioning, hidden line, shaded images, dimensions, and many others you can do. All right, with a geometric model all these functions are allowable. Under manufacturing, you can classify the part, you can plan the process based on the model over here. You can plan all the different processes. You can generate your numerical control data and verify it. And then you can generate program generation. So this is working towards production. So under production, you can generate the bill of material table, which in return helps you to generate the material requirement, manufacturing resource requirement, okay, MRP and everything. So this will tell you, if you have, let's just say this product to manufacture, in what batches we are going to manufacture, every 3 weeks once, every 1 month once, whatsoever, and then how we're going to manufacture it. Are we bringing in the raw material every 3 weeks once, every 6 weeks once, and then who are the production people needed, what are the resources needed, utility needed, storage, so multiple things, okay, because all these things can be scheduled. And then we can inspect and quality control the product. So you would have seen this inspection machine, uh, coordinate measuring machine in chapter 2, right, which inspects the quality of the, for instance, the dimension of the product. So other than that, you can actually inspect not only its dimension or model itself, you may also inspect its production, right? You can have X-ray inspecting machines through augmented reality. You can also have, programs where you can actually code it in such a way you can detect whether labeling has been done well, sealing, so many other things, right, can be done with your geometric model. And in the end, you can compare your produced part with the design intended. So now, moving on to what geometric models are, we have two types of model, 2D and 3D. So we would have gone through all these things in the what we call the overview of chapter 1, which actually covers the overview of all the chapters, right? So basically that would have been done, all right? So we have three types of geometric model: the line, surface, solid or volume. So what is the line, surface, right, and solid or volume model? So the first picture over here speaks about a line model, which simply reflects to a wireframe model. So this is nothing but a connection of points with edges. So this will just basically be lines. Now all three models, the purpose and the objective is to give us a visual representation in three-dimensional space. So the wireframe model is the simplest and easiest representation, right? But it can create ambiguities, like you can see over here. You do not know whether this is from this side or it's in the internal side. It can give you a rough idea, but not the full idea. Okay. Then we have the, sorry. And then we have the surface model. So the surface model is a covering of surface, all right? Surface 1, 2, 3, 4, all right? It is more complete compared to the line model, a better representation of the 3D product is actually available. But you can't use this to actually derive mechanical properties really as per se. Both these models cannot work for that. So finally, what we rely on is our volume model, where it is actually done based on volume 1, volume 2. So this is what you are doing in your CATIA. You're actually designing based on volume. So surface is not in our syllabus, neither is line, all right? A line model is incomplete until you create at least a surface or a volume. So moving on to the wireframe system. So as I mentioned earlier, it's a 3D representation, visual presentation. And the difference between 2D and 3D is 2D, we get our drafting, right? We get all our drawings. And the 3D is you can see it in 3D space and it has X, Y, and Z coordinates involved. So how the wireframe model comes up is when, let's just say I tell you, or I tell even young children, okay, can you show me what you're planning in your model or your design? So, they take matchsticks, sticks, or whatsoever and try to build. So in that same concept, the software was also built trying to actually display a 3D shape. So using metal wire. So basically this model is actually a collection of points, or what we call vertices, with a set of edges. And it uses geometric entities like lines, circles, arcs, standard shapes, all right, existing in the system. So these are some examples where you can see, now this is a car, you're trying to present something, but you know how this, let's say this tire here crosses into the solid. So this kind of things, you may not be able to actually visually discriminate. So in the case of wireframe model, the computer has no knowledge on the surface shape, so it will not know what is solid and what is not. Hence, it leads to it becoming ambiguous, or like what I said, we don't know whether this area here is inside or actually outside. So that kind of ambiguity can appear. And it tends to be not realistic. So these are the disadvantages. So, and becomes hard to interpret. So, and there is no ability to determine computational information. As I mentioned, all the mechanical properties like mass, volume, and all those things. So basically, it does not guarantee that it's correct, complete, and definitely not manufacturable. So what does it give you then? It's easy to construct when let's just say I give you all the mini project, and then I said, please tell me what you're planning to do. So you all would just sketch roughly. So that sketch is this wireframe, which gives me a rough idea on what is going to take place. Easy to construct, economical, and requires small memory usage, right? And we can always use it in previewing something. And it allows you to draw impossible objects, but in return, sometimes it becomes a problem. So an example of a wireframe model. And now we move into surface modeling system. So this is an upgrade from the wireframe system, trying to create a more wholesome image for models in general. So the surface model is constructed essentially from surfaces such as planes, rotated curves, which are called ruled surface, and complex surfaces. The aim for the surface modeling, we want to define the surface form and define the model in a whole. Okay, and we want to be able to calculate accurately the x, y, and z coordinates of any surface. So why do we say this? Because in general, surface modeling is linked with complex shapes, all right? Very complicated shapes, like car bodies, ship hulls, die cavities, decorating surfaces for aesthetic reasons. So these are all different shapes where you actually cannot really define. It's not like a sphere or, a round or an ellipsoid. It is wavy, complex, crisscrossing few surfaces, right? So in these cases, we can't actually really, define or redraw, because you don't know how many curves are included. So in such situations, how do we then model these things? Okay. So how do we model is we actually model them through a series of control points and boundary condition, all right, to actually form that curve. So this type of modeling, right, used in CAD system is what we call freeform modeling, right, where it uses concepts like Bezier surface, B-spline surface, NURBS. So these are all formulations, mathematical formulations to build your curve and later on your surface. These are ruled surfaces where you would have actually done, sweep. Probably in class you would have done sweep or rip. You would have done revolve or shaft. Maybe some of you in your class may have even gone on to have been doing multi-section solid or loft. Okay, so this is actually an example of sweep where you have actually the cross section and it's swept across this U trajectory. So we have the classification of surfaces, and the surfaces are classified into three. Where's my mouse? Okay. First one is planar surface, which means plane, flat surfaces, all right, where we have the polygon and polyhedra, all right. And then we have the curved surfaces, where you have single and double curves. So a single curve is like, let's say, a cylinder. You see, if you have, see there, my drawing is so poor. Oh dear, wait. Okay, this is off. Let me rub just a minute. Okay, so let's say you have a cylinder, so try to get it as well as possible, right? So you can see the top of a cylinder, although it's made out of circles or a curve, right? But it's flat. And then this side is one curved surface. So we call it single curve. Same thing for cones, you know, this is how a cone would look like. The bottom is flat and it's one single curve. So a double curve is like for a sphere. Let's say you have okay, so let's say you have one curve and another curve, and hence the 3D version of it would be a sphere. Okay, so these are double curves. So like this, we have ellipsoids like this, all right, paraboloids, toruses, and everything. And then we have the third type, which is the free form. We call it the cone surface, and these are formulated purely by formulations, all these formulations which I mentioned earlier. So they don't go based on shapes. They are any type of curves which just moves freely. All right. And the lofted surfaces come under this. So these are examples of curved surface where you have a single curve. You can see one single curve with a straight line. You know, this is also a single curve with a straight line, although the curve is actually two different dimensions. All right. So this is called like lofted single curve. And then you have double curve where you have this and this to form a surface like this and this. And then you have translation or revolution where you have planar, single plane, and it is actually revolving, right, 360 based on this shape here. Okay, so this is a revolved curve. So creating the surfaces is basically being done by the CAD softwares. And this kind of commands are actually incorporated into your softwares because it is the niche thing in the market. It is basically the demand for almost anything and everything that you have. Like if you can see over here, I'm trying to show you just a pure plain pen holder. Okay, so this is a very inexpensive, cheap item. And even in this, you can see there is curvature to the surface to enhance its image. And this curvature is just not any single curvature. It's not like something where just a corner was rounded. It's not going to be easy if I give you this and say, redraw this. Okay. So in that similar manner, right, everything moves about some kind of beauty where the curvature is given. So earlier on, we discussed about the classification of surfaces classified into planar, curved, and freeform. And now we will look at the resulting surfaces from these classifications, which is also divided into three. We have generic, freeform, and derived. So when we look at the generic surface, right, so this is created by sweeping a generator curve along a vector or about an axis, like we saw earlier on. So the types of generic curves, all right, we have two types. The tabulated cylinder, which I showed just now. You see you have a cylinder like this. So it is a planar surface which is swept along a vector. Okay, so the magnitude of the vector controls the size of the surface. Or you could have a tabulated cylinder like this, all right, which is swept along, you can see now, a curved path, all right. So this is the vector of movement. And then you will have a surface of revolution, okay, which you have, let's just say any product like this, and it revolves around an axis. So when it revolves 360 degrees, so you will get something like this as a product. Okay. This is a tabulated cylinder. This is a direct movement. This is a curve, all right, which is also multiple curves put together. And this is, you see, this type of curve, okay, with a straight line. And this is a revolution or revolve. This particular trajectory revolved 360 degrees. The second type of derived surface is the freeform surface. So usually you use more than one curve to create such freeform surface. In this, there are 5 types. The first type is the ruled surface, where it is ruled by true boundary curves. Okay, you have the top boundary and the bottom boundary, and the nature of the boundary will decide, right, how the surface forms. Like you see, this is the first curve, although it's a straight line. The second curve is a curve, and hence this will define its surface. The second type is what we call a surface patch. If the earlier one was bounded by 2 curves, this one is bounded by 4 curves. So an example of this is, if you all can see now, I have a paper with me. A paper has 4 edges, right? 4 sides. So if I want to make this surface now, this is like a flat planar surface. If I want to make this into a curved surface, you see now I'm actually rippling my paper in a funny way. So what you would notice is, you would notice that this edge is curved, this edge has a different curve. So as you ripple this, you form a different type of surface. So the 4 bounding corners will actually form the type of surface. The third type is a net surface. So this is created from a network of curves, multiple networks creating a surface. The fourth type is a swept surface, like I mentioned earlier. We have a cross section which is swept across a guide curve. So like even a cylinder is a cross section which is swept along a guide curve. So hence you will get a cylinder. The fifth type is a lofted surface, where you have multiple cross sections swept across a guide curve too. So a multiple cross section at different planes swept along a linear curve will give you a linear shape like this. A multiple curve at different planes swept along a curved area will give you a surface which is curved like this. So this is what we call lofted, where it is actually designed in multiple planes. Now the third type of derived surface, so all these things you would have seen in your Katia or are about to see, okay? Now the third type of derived surface is the offset surface, okay? So the offset surface is basically derived from a particular surface where you're just going to actually copy the surface over. So it could be just a plane. You all would have done, creating reference plane, creating reference surface. So basically it's just offsetting a particular surface. The second type is a fillet surface, where you have 2 surfaces put together and you're trying to round the corners. So the concept is as if imagining a ball moving around that edge. Okay, so you get a fillet. So it's like a blending operation. So this and the one before this, we call it derived because it's derived from an existing surface. Seeing the concepts here. Now we move on into the free-form surface. So earlier on we talked about classification. So this is the third classification of surfaces. We are not talking about resulting surface now. We're talking about the third classification of surfaces, which is now Bezier. So what is Bezier, right? Basically, if you want a more free-form design, not contained to a particular shape, so we will use free-form curve formulations. So basically, free-form designs gives you better aesthetic surfaces, better finish to your surface, and it satisfies requirements of customers and it gives you flexibility in creating your surface. So this concept, right, of Bezier curve was actually first formulated by P. Bezier, and he's the designer for the French car company Renault, right? So he invented this way back in 1960s. So what it does is it uses vertices as control points to approximate the curve. So this is what happens. Now that you have a curve over here, it will link, the curve is actually generated based on control point 1, control point 2, control point 3, 4, and 5. Okay, and these control points are linked by what we call these control polygons. And the curve is only joined to control point 1 and 5. Okay, so now that you have a curve like this, let's say we want to change the shape of the curve. How are we going to do it? We are going to move the control point. So let's say here, the earlier control point was here. If I move this control point to a new place, you can see now the entire curve tweaks and forms this new shape. Hence, the more the control points, the greater the flexibility of the curve in moving its shape. And this is if you're going to actually see it from a surface point of view, then we call this surface polygons. This, all right, to create a surface using the Bezier concept. Now, what is a B-spline curve? So if we saw earlier that Bezier is actually formulated in this manner. So these control points are actually having coordinates x1, y1, z1. Okay, this will be x2, y2, z2. Say, pardon my writing, and so on and so forth, right? And these things are formulated on your Cartesian coordinate. Now, why we move on to B-spline, all right? Because the way Bezier works is the more you want the flexibility, the more control points you need to increase. And the more control points you increase, it will increase the polynomial of the curve. So what is polynomial increase? It means you increase the power of the order from 1 to 2, which is quadratic, third polynomial, which is cubic, fourth polynomial, and go on and on and on. In this case, the polynomial of this curve, we have 1, 2, 3, 4, 5 points. 5 points. Hence, the way the polynomial is actually formed is actually the points, which is n minus 1. So you get 4. So this equation is going to be on the fourth order. If you want a more flexible curve, it will result in a more complicated formulation or equation. Hence, in order to actually tackle that, alternatively, the B-spline method was recommended. So how does this B-spline work? The concept in the B-spline is the curve is attached to the control point. Each control point attaches itself to the curve. Hence, when you move, let's say, this control point to here, so what happens is the whole curve doesn't move. It will only move here. Okay, pardon my drawing. It will be a nicer, a nicer curve lah. Okay, let's see here. And this portion of the curve will remain the same. That's the concept. So the formulation is only going to be disturbed in this region and not the other regions. So B-spline's initial formulation is harder than Bezier's, but if you're going to make differences in the curve, it's a lot easier to use B-spline because we are only locally making differences, not on the global aspect. Okay, so that is the difference between Bezier and B-spline. For our learning purposes, right, to understand and appreciate this entire curve formulation, we come into CATIA, we just draw a line, we draw a square, we draw a spline, and we don't even know what was put, what was the effort put to actually form that software. So for that purpose and to understand how it works, we are going to actually study curve representation. And this is the one I said we will cover in our second class. So, and for that curve representation, we are going to study the Bezier curve, okay? Because it's a simpler formulation for us to understand how the movement is made. Okay, just a minute. Okay, so I will skip past this because this will be, covered in our part 2 class. And now we come into the application of surfaces. So the application of surfaces, why do we even need these surfaces and its applications? Because we want to create what we call a photorealistic image by applying foreground, background colors and everything. So when we have curves, right, because the areas are up and down and not so direct, it creates what we call, different lighting and shading and everything, which enhances the beauty of the curve. Reason why anything curved looks more beautiful than a plain object because of the way the light reflects, basically. So it gives us the flexibility and freedom to, beautify our object, right? So this is actually a very powerful industrial tool to make our products more desirable in the eyes of the customer. So these are the applications you can see. You can do all kinds of rendering. Okay, so that is for surface. So we discussed line model, which was under wireframe. We discussed surface model, and we discussed a few types of surfaces that we are going to create. And now we discuss solid modeling, which is what will be relevant to you all because you're doing this in your lab. So what is this solid modeling? It is basically a computer description, right, of a closed solid 3D shape, all right, represented by a data structure, all right, where you can actually understand the mechanical properties, you can impose 3D material on it, and you can actually deal with that virtual model as if it's a real model. So it's also composing of primitive objectives. So what are primitive? If you see the word attributes, primitives in design, it speaks about our basic shapes like circle, curve, line, arc, triangle, cube, rectangle. So, I used certain 3D examples and some are 2D examples. So in the case of a solid modeling, the model is usually complete and always it's unambiguous, it's clear cut, physically realizable, and you can modify it. Okay. Now we will discuss about two types of solid modeling. The first one is what we call the Boolean combination or Boolean operation, right? So you can see now, these are, aspects of solid models. It allows you to actually take upon any kind of manufacturing task, from design to programming to analysis to manufacturing. So, as I said, we have two types of solid modeling here. The first one is the constructive solid geometry or the CSG model. And the second one is the boundary representation model, which is called the BREP model. Okay. So what are these? We'll first describe the CSG model. Just let me take a little bit of water. I think someone needs to mute. Okay, so the CSG model, right, it actually is represented by using a tree structure called a CSG tree to define a solid model part. So how is CSG done is basically modeled using solid primitives like block, cylinder, cone shapes, existing shapes. And it goes about this concept of Boolean operation where you can actually have operations like add, union, subtract difference, and intersection to create your solid model. So we use all these different solid primitives to bring about different combinations of a model. So look at this 2D representation. We have a square and a circle. Now, if we combine, you will get this shape. If you subtract, depending what you're subtracting, so in this case, we are subtracting the circle from the square, you will get this shape. If you intersect, then it is actually the overlap of this, right? So you will get this shape. Now, a 3D version of it is, let's say I want to design this, 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 and this. So the way you all have to do it in CATIA is you have to first design this and then open a new model and design this, open a new model and design this, then open a new model and design this. But let's say I want this 4 shapes within 1 or 2 operations. And when I mean 1 or 2 operations, I mean I only need to design this block and this block. And after that, I can cross combine them to actually create these various shapes. So I can actually have, a union operation where you can get this kind of shape. I can have a subtract or difference operation where I can get the shape. An intersection operation where I can get either this shape or the shape. All right. So, sorry, this is intersection. Both of these are subtraction. All right. So it depends on what you're subtracting from what. So in this case, it is important to specify the base model. So when you specify the base model, you can only differentiate or subtract the new model from the base. So in this case here, all right, the base model was the first block. In this case, the base model was this block. Okay, so this is the concept. Where is this useful and why is it useful? So if you look at this particular image over here, here we have what we call a helical spring. So a helical spring can be actually designed in CATIA. We can visualize designing it mechanically. Now, the next object over here is the human head. All right. Now, this is an organic shape. Okay. And now, if I want to design this in CATIA, I'm going to have my obstacles and my design is never going to be as exact as this particular shape over here. Can any one of you tell me why that will happen? Why my design is not going to meet the final shape? Definitely my helical spring I can pass, but this one I will not get it. Why? Anybody?
The shape is too complex.
Okay, shape is too complicated. Can you elaborate further? What exactly is the complication if you want to actually do it? Basically, when you design, what do you need when you're designing?
Dimension.
Dimensions, right? So can we get exact dimensions of this? Now we are trying to get the depth of the eye, the bridge of the nose, the curve of the mouth, and this and that. Are we going to be able to really trace everything out? No. Okay, it is going to be very difficult. And even if we do, let's just say now you need to make another human head, my head and your head. So you manage to get my head out, and if I'm going to change it to your head, it's just not changing, one dimension here. Like in this case, you can just change the radius and you get a thicker spring. You change the pitch, you can get a wider gap. You increase the pitch, it will adjust the spring. And then the height you can change and you can get longer, shorter spring. Now that's not the case with the head. It's going to be harder to construct, right? So organic shapes like this, what do we usually do? We scan them, or we actually reverse engineer them by scanning the entire data in. How do we scan them? We use multiple digital points, right? We actually, either have a touch probe on each of these areas, all right? As many data points as possible will ensure that your model is closer to accuracy. Or we can just actually do rough scanning, right, and import the surface image and then create a solid outcome. So why this Boolean operation may prove to be useful? Because if you have such shapes and you want to combine and get, 1, 2, and 3, certainly you can't do this with your normal boundary wrap modeling. Boolean modeling is the one that's going to give you this kind of shape, this kind of figure, and this kind of model. So it allows you to actually mix match organic and inorganic shapes. Other than that, like I mentioned earlier, it allows you to sometimes model certain things in a two-step method without going through multiple design steps. But it is not always useful, because each time you want to do Boolean, you need to have your basic shapes ready, and it's only limited to that basic shapes. So you can see over here now, if I want this shape, the shape, the shape, and the shape, I can already understand immediately. If I had done something like this with Boolean, I can get three models at one go just by designing only two parts, 1 and 2. Okay, so this is how an expert designer will identify the difference and sometimes work towards it. Okay, so not everything can be done in this manner, but then when you identify and look at something, you will know when to use Boolean and when not to use it. So over here, I have actually inserted a YouTube video, all right, on how to actually go about Boolean operation. But later on, I will also share the video we did this morning. So I'm not going to go through Katya again. I will just play the video a little, all right, for you all. So basically how this Boolean operation works is wherever there is a boundary crossed, like you see, this is one end of the boundary, this is another boundary cross, this is another boundary cross, right? At each of this boundary cross, if I want to have an intersection, it will take this part. If I want to have a difference, then it will just take, let's say I want a difference. Okay, I'll change the ink color. So the difference will be this, or the difference will be this, like that. Okay, so it depends on the boundary edges. So this is the CSG tree that I was talking about just now to build a model. So you may get this kind of questions in your exams where you need to build CSG trees, right? So this is a CSG tree. Basically, if you're given a model, you need to actually tell us how you will reach this final outcome by first deciding the base model, which in this case is the block. And after that, followingly deciding the different primitives needed to be added, to be subtracted, or to be intersected to finally reach your final goal. Okay, so in this case, right, we are going to add another block over here, and the operation here is union or add, right? And then we are going to have a cylinder to be removed from this model right now. So the operation is subtract or difference. And then another block over here, okay, this block, subtract, and then a cylinder over here also subtract, then you get your final product. So basically it's a step by step, okay? Point to reach your final model. It's like how you do your BREP, but this time around you are doing it with already existing shapes. So this is for Boolean operation. So basically it's like a binary tree consisting of the different steps. So this CSG concept is actually available in our solid modelers, all right? It enables one to build the complex shapes quickly but only within the limitations of the primitives available. So primitives are, these are primitives or attributes in 2D. Okay. Now we move on to BREP model. So what is a boundary representation model? So a BREP model is a type of solid modeling where we actually build the model based on boundaries or enclosing surfaces. First enclosed by vertices. Vertice means point. Okay, let's say I have 4 points. And the 4 points are connected by edges. So hence I get a square. And these edges, all right, they create the boundary of the first surface. And you may actually sweep it along a particular vector to get a final solid. Like this. So you have your 4 corners. And so this is what you all will do in CATIA. Then after that, your 4 corners, you will just draw a square. And then you will take the square, you will exit and you will go out and you will give a vector. And it will extrude. And now it will finally form surface 1, 2, 3, 4, 5 top surface and 6 bottom surface. So this is the idea of boundary representation model. A model which is represented by boundaries. And these boundaries are confined by the vertex or points, edges, which creates boundaries. And finally, and these boundaries later can be represented as surfaces. And this will lead to a solid volume. So, do you think in CATIA we are using Boolean modeling or BREP modeling?
Boolean.
B-rep.
So some said Boolean, someone said BREP. Okay. So the answer is actually BREP because I will later show you that Boolean means how to do it. So BREP means like how we will do, straight away we will actually build something. Whereas in the Boolean operator, we need to actually build two things and then combining those shapes only, we will create Boolean model. So in our solid modeling packages, we basically rely on the BREP types. But the Boolean operations are incorporated in for all the alternative functions necessary. So now we move on into what is the application of our solid model. So why do you need solid modeling? We need it for all these factors, right? So that we can visualize our model. Like we started off the class by saying that, right? We want to have a 3D visualization of our model in order to be able to calculate mass property and check all the mechanical properties present within a model, and then produce assembly modeling and then check interference, kinematics, and then draft a model so that we can have a full documentation to be sent for production. Perform rapid prototyping, which is like 3D printing and all comes under rapid prototyping, manufacturing reasons, okay? And then analyze the model and its structural integrity through structural analysis. You can do stress, strain, heat, drop tests, everything. Study the mechanism of the model by visualizing it, looking at its kinematic simulation. And then we can also build tool designs. We can check the quality of our model, right? And generate production codes, okay, NC codes, and then also check the quality through its dimensions and all. Perform robotic simulation and virtual prototyping. So you should be able to understand this and elaborate further. So this slide over here, actually this is linked to the earlier slide. It just speaks about the same thing again, the surface connectivity now in the aspect of a surface. When earlier on we were talking about curves, now we are talking about surface, which only means that we are looking at it from a 3-dimensional point of view. And you will realize in next week's class when we are doing our formulation that in surface modeling, we don't directly view it from the Cartesian X, Y, and Z coordinate. We are going to actually have a parametric transformation into another representation. Okay. Why do we do that? Because these surfaces are described in a different language compared to our coordinate language. So hence, this will describe the surface connectivity. Now we move into hybrid modeling. So what is hybrid modeling all about? Okay. This is something like what I mentioned earlier on. If you want to actually design organic shapes like a tree, your bone, your skull, or even what was initially a mechanically built shape like car bodies, bumpers, bonnets, and all those things, right? Hybrid modeling comes into play. And what do? They actually use the digital shape sampling and processing method, okay, to import all data points on a product, as many data points as you can actually gather from one particular product, either through probe touching or scanning or anything like that. And it's brought in as a surface model, and later the surface model is actually embedded to create a solid. So the DSSP converts 3D scan data into digital models. And once you have your digital model, it is your CAD model already. And what can you do with it? You can do everything you want to do with CAD. You can visualize, you can analyze, you can manufacture, you can send it for coding, cutting, everything. Okay. So the traditional CAD is good if you can model from scratch. But when you can't model from scratch, now hybrid modeling definitely fixes these limitations because it reduces the time to reconstruct the complex CAD object. So if I ask you to again, right, I say model your bone, you're going to scratch your head. I'm going to scratch my head because we are not going to be able to do it easily. It's, with all the funny curves and dents and everything. So when you import the model in, then you can start doing other things to it. What can you do? You can save the data. You can do drafting to the solid model. You can also analyze the solid model. Like if I take a hammer and hit my bone, so what force is it needed to break my bone now can be studied already. Okay, because you have imported the model in, right? So like that, many things can be done. So what is to be imagined over here is, let's say we have a car body, a car bumper. Okay, so I said, okay, please go and take the Perodua Myvi bumper and study it. So if you're going to try to model the Perodua Myvi, you will go to the bumper and you'll try to measure. How many measurements can you take? You may be able to take more direct dimensions, but all the indirect, hidden curves and everything is going to be hard. So if you actually scan the entire model using DSSP, once you import it into CAD, then what you can do is you can start analyzing the bumper. So let's say I want this bumper, this round, I want to increase its radius. I want to add a cut over here to reduce the material, and I still want to see whether the bumper can withstand crash. I want to make the bumper thicker, thinner. All these things can be studied, okay, once we import the model. So this is by far the very powerful advantage of digital shape sampling process, or what we call reverse engineering, which is widely used in the automotive, aerospace industry, biomechanical, biomedical industry, and all these things. Okay, basically we want to know, right, how each of our bone is going to be able to tolerate trauma, biomedical. So this is what they're doing. They're using cadaver models, reconstruct and study. So all those difficult to identify and quantify parameters can be actually quantified when you digital shape sample it. So the applications, it's applicable to capture physical designs and prototypes, and then you can reproduce legacy parts and toolings, all these ancient parts, which you don't have data and drafting data upon. It can be reproduced. You can replicate complex and organic shapes, like I mentioned earlier. Prepare as build models for CAE. As I mentioned earlier, you can do analysis. You can mass customize unique components like dental application, hearing aids, which has a lot of curvature, right? Once you bring in your model, that's it. You can just completely mass produce it, okay? And you can preserve historical and cultural artifacts because naturally we don't have any CAD data, not even drafting data. So when you digital shape sample it, you actually can reproduce the entire drawing. So this is an example of, right, modeling an impeller, a difficult model, right? So what are we going to do? Imagine you have to design this. So what angle this turning, how it's turning, it's a real headache. So what they do is they scan the impeller, right, this entire shape. And then when you scan in, now there is a glitch over here where sometimes not the full data gets scanned in. And you can see right now, right, you have these yellow areas, okay? So what happens is when it's scanned in, all these yellow areas are what we call incomplete surface. That means like holes, on your model. What do? They actually trace the boundary, the outline, once they draw it, right? And then you can see already, they will extrude a solid or a surface. So you would understand, right, when we do actually modeling, okay, in all your solid modeling that you have done, if you're going to extrude, let's say I have a square and I'm going to extrude something inside this, you will notice as you actually extrude inside the solid and solid merges. So it doesn't matter. It's not like I have double mass inside here. In solid modeling, when I merge something, it's still seen as a single mass. All right. What is extruding outside is seen separately. So that's the whole concept here. They will merge and clean up all these surfaces by trimming, blending, and everything. And finally, you will get a smooth surface. So once the smooth surface is obtained, only then you can actually send it for analysis where you can mesh. So you can never mesh any product when there is a gap in its boundary. And then when you do meshing, you can run analysis. So this is an example, right? So an impeller is actually seen to be a complicated model, and hence we can use this hybrid modeling for these purposes. What are the advantages of hybrid modeling? It uses 3D investment where you can actually, once you import the model, you can do everything you're doing with CAD on that particular model. It helps you to create new designs quickly. So what if you want to actually imagine designing this impeller, it may take you weeks or months. Within days you can actually import the model. So it needs, of course, a specific tool and software and everything, but it's possible. And then you can produce native parametric CAD geometry, right, for each of your models, and you can generate accurate results, because if you're trying to design this, you're never going to be as accurate as you scan the original model in. Okay, so these are all the advantages of hybrid modeling or reverse engineering, which is commonly right now used in the industry. Okay, so we are done with chapter 4, part 1, all right, which discusses all the solid geometrical modeling techniques. So do I have any questions from you all so far?
I think no, madam.
Noah, anyone else? Nobody?
No.
Okay, okay, so I will stop the recording.